Okay, so let's see. So next we're going to look at our original function that we just had before. Okay, coming back to the Charlotte example. There's our function that we wrote. Okay, they're asking again, what is our growth factor? We already wrote this, I think, a couple slides before. So our growth factor is 1.03. Okay, and our growth rate is 3%. So it's either 0.03 as a decimal or, well, they want it as a percent anyways, 3%. Growing 3%. All right, so let's use this to figure out what our population would be in 2015. Okay, so we're really figuring out, let's write it in function notation. What we're really doing is finding P of 7, which means we're plugging in 7 for our years. It's 7 years past the initial year. Okay, and this would come out to be about, in thousands, they're putting their answer, 844.9 thousand people. Okay, so the next thing we're doing is taking a look at the graph of this and finding some other things. So take a minute and put those windows in and graph that function that we've got right up there, our Charlotte function. And so we determine P of 0, that's part C. There's a couple ways we can do that. We can use the graph. Okay, we know right from the equation what P of 0 is. That's our initial. Okay, P of 0, if I plug in, let me just show you algebraically, but we can see it right away anyway. This is kind of just to show you why that works out. If I plug a 0 in for t, remember anything to the 0 goes to 1. So we end up getting 687. We knew that. We knew that was the initial population in Charlotte in 2008 in thousands. Okay, so that this really means, what's the practical meaning? In 2008, there were 687,000 people in this Charlotte, North Carolina. Okay, use the model to predict Charlotte's population in 2018. So 2018, and that one would be 10 years after the initial, so I would be finding P of 10. Okay, so one thing I can do is just do it algebraically, okay, plugging in. Another way I can do it is if I go on my graph, when I'm on the graphing calculator, I could go to table. Remember, then table, you get a list of x's and then y1s, and you scroll down and find where x is 10, and then figure out what is y then. Okay, it's going to come out to be about 923.3 thousand. Okay, so once you have it into the calculator, use some of those functions. Use the table function. You can use the graph and trace it, although that's not the best way. And you can also use under calc on your calculator, you look under value. It lets you plug in any x value and figure out the y value for you. So that's the third option. Okay, so they're having you verify on the graph. So if you go and trace on the graph or use what I was just saying, the value, and plug in 10, you'll have your graph like this. Okay, and if you can either trace it or use that value, you'll end up getting the ordered pair on the bottom of the screen. Again, it will also show up on the table, so either one of those is fine, but just showing that after 10 years after the original, we'll have 923.3 thousand people in Charlotte. Okay, so use the graph to estimate when the Charlotte's population will reach 1 million people. Okay, assuming it continues to grow. So remember, so P of t is the number of thousands. So when we're doing this, since they're giving us 1 million, they really want P to come out to be 1,000, because in this function, remember 687, we have it as 687, not 687,000. So 1 million would be like 1,000 thousands. Okay, so use your graph. You can use the table and kind of scroll down when you find that 1,000. You could also go into Y2 if you wanted to and put in that 1,000 and find the intersection of the lines. That gives you an exact way. So this happens when T is about 12.7 years. Okay, so that's really about, if I add that, about 12.7 years or about 13 years, we're in about year 2021. Okay, so we're just doing one more of these. Evaluate it when P of 32. So if you either plug 32 into their function there or use your table and scroll down to 32, you end up getting 1,669. Okay, so that's really, again, this is in thousands, so this is really 1,769,000 people in this year, which would be 2040, because it's 32 years past 2008. Okay, use the model to estimate the population 2010 and 2030. Which prediction would you have more confidence in? Why? Okay, so we just found both of these. Oh no, wait, 2010 we already had, I think. 2010. Whoops. 2010 was 2 years past the initial, and that came out to be 728.8 thousand. If I find 2030, I'm really finding P of 22, and that ends up coming out to be really, if that's in thousands, we're really talking about 1,316,000. So which one is a better prediction? Well, if you look at the beginning, we don't know how long this growth is going to continue. So we're always much more confident about that earlier year because that was closer to the original data set. So we would say we're definitely more confident about this one because once we get to the 2030, we're extrapolating quite a bit. So that growth rate might not maintain the same amount for that long. Okay, so this is the next part is the same exact thing you did in the last activity, that finding that doubling rate. So they're asking how long does it take? So we're really looking for the P to come out to be. We're looking for when does the P come out to be 1374. That would be double the original. Okay, so again, if you could use your intersection, you could go into Y2 and now put in 1374 and figure out where do they intersect. Okay, you could scroll down your table and kind of narrow in where that happens, but this happens if T is about 23. Okay, so that's about 23 years past that initial. Okay, so again, you can use the intersect feature on the calculator or the table. You can trace it again, but you may not get right near 1374. The intersect is going to give you the most exact answer because it gives you an exact ordered pair where they intersect. Okay. Okay, so the next example that they have us is for a growth decay one. So let's do one of these and then we'll stop this activity there. Okay, so you're working at a wastewater treatment facility. You're treating water contaminated with 18 micrograms of pollutant per liter. Your process is designed to remove 20%. Okay, so we see this one, we're not growing, this is a decay one. So your goal is to reduce the pollutant to less than 3 micrograms per liter. So what percent of the pollutant present at the start of the treatment remains at the end of the treatment? Okay, so what they're saying is if you're, each treatment that you do, if you're decreasing the amount of pollutant by 20%, how much are you keeping? Okay, so remember we talked about this last time. If it's going down by 20%, you're really keeping 80%. So 80% remains each time. So the concentration of pollutants is 18 milligrams at the start. So let's figure out what happens at the end of the first treatment. So if I have 18 at the beginning of that treatment, so I'm not going to multiply by 0.20, okay? I'm going to multiply by how much of it remains, okay? Because if I multiply by 0.8, that means I've lost 20%, which is what I want. And this comes out to be 14.4 micrograms still left after the first treatment. So now we're going to use the table to figure out, well, how much is left after each additional treatment. So after 2 treatments, again, if I'm doing that 2 treatments, I'm taking my last answer, 14.4, and timesing it by 0.8 again. And that's going to end up getting me 11.5. And after 3 treatments, if I take 11.5 and multiply that by 0.8, I have 9.2 left. And then 7.4, 5.9. So now let's write an equation like we did in the previous ones, in previous activities. So we know the initial amount, okay, if our n value, that's the number of treatments, if that is 0, we should get our 18. That's our initial. So our initial is 18. Okay, each time we're going to end up multiplying by 0.8 or 0.80 to show that's 80% we're keeping to the n. Okay, so in this one, let's kind of talk about, again, what we did before. Let's talk about decay rate versus decay factor. Okay, the decay rate is how much what is it going down by. Okay, so each time in this one, this is going down by 20%. So that's my decay rate. But in order for me to do that into a function, that means I'm keeping 80%. Okay, so really, this is really going to be 0.80. That's what's going to go into the equation. Okay, so I'm going to look at example 5. Determine the decay factor and decay rate of that function. Okay, so we know, again, 123, and that would be our initial. 0.43, if I'm multiplying by 0.43, if that's my b, that means I'm keeping 43%. Okay, which means I'm decreasing by 57%. So that is that's my, in this case, decay rate. Okay, so my R value, what they have right here, would be either 0.57 as a decimal or 57 as a percent. So what if our decay rate of a function is 5%? So if we want to go down by 5%, okay, each time, well, what do we have to do? We have to, our rate is 5%, but our decay factor is 0.09. This would be our decay factor. That's what I have to multiply in order for it to go down that much. So what's if the decay rate is 2.5? What's the decay factor? Okay, so if I want to keep, if I want to go down 2.5% every x value, well, how much am I going to keep? I'm going to end up keeping my b would be, I want to keep 97.5%, or multiply by 0.975. If my decay factor is 0.76, what's my decay rate? Okay, so this time they're giving us, if this is my factor, okay, if that's my b, if I'm multiplying by 0.676 each time, how much am I losing each time? So that would mean my R value would be 0.24. I'm going down by 24% if I'm multiplying by 0.76 each time. Okay, so let's come back to this function one more time. So use that function to predict the concentration after 7 treatments. So we're really finding C of 7. And we're going to do 18 times 0.8 to the 7th. And we're going to end up coming out to have 3.7, whoops. 3.7 micrograms still left after 7 treatments. Okay, so the next part you're going